A2 Further Maths, First Order Differential Equations. Okay, so what I'd like you to do is just using your skills that you've just learned about integrating factors, just have a go at solving that differential equation by using an integrating factor. Pause there, have a go at that yourself. Okay, so let's see what you did then. So hopefully, because it's an integrating factor, you considered, it's already been nicely set up for you, and you can still see the formula at the top of the board, that this 2x is the px function. So that's the bit that goes in the integral. So therefore your integrating factor is equal to e to the power of the integration of that function just there, 2x. So once I knew that, then I can actually solve it. I can work out the integral of 2x and I get my integrating factor of e to the power x squared. Then once I've got my integrating factor, you can multiply that through. Okay, so you multiply it by through, and this side just here is going to end up becoming the same as the product rule in reverse. So therefore that's why that gets IY just there. Okay, so I've done the integrating. Once I've done that, I can then concentrate on this side. So I'm integrating this part just here by multiplying it by e to the x. It looks a bit messy, but what I can do is I can write this out as two separate integrals. So it's 3 times the integrating factor there, and it was 6x times the integrating factor here. And then why I've done that is because now I can solve these two. Okay, so I can solve them using a substitution method or an integration by parts, and I could solve it with both of them. So the first one, e to the x squared, I'm going to think about writing that as 1e to the x, and that might be enough of a hint to start you off. So if e to the x squared, I can use it as 1e to the x. Then what's going to happen is I'm going to get du equals 2x e to the x squared, and I'm going to get v equaling x, which makes it seems like it's gone more complicated, doesn't it? It does look like it's gone more complicated. So what I've done is I've done that, and the reason why I've done that is because then when you actually work this thing out, right, because you've worked this thing out, you'll notice that actually this part and this part are the same. Right, these two bits are the same. Notice the 3 times the 2 is going to get you minus 6. With that plus 6, these two are actually going to cancel each other out. So what seemed like an almost impossible integral to do actually works out quite nicely, because just concentrating on that one bit means that these two cancel each other out. Now I wouldn't expect you to notice that. I didn't expect you to actually finish it off yourself, but you would get a hint to that potentially in the exam. You might get told to do that bit first, okay, with integration by parts, and then spot they cancel out. So what happens then? These two are going to cancel out, and I've got the solution then of just this bit. So y e to the x squared is equal to 3x e to the x squared plus my constant of integration. Once I've got that once I've got that part, if I needed to rearrange it and write it as y as a subject, I could do. All right, I could write the general solution there by dividing by e to the power x squared. Notice then I get c e to the minus x squared for that bit. And there we go, I've got my general solution. So that's not anything new. You've practiced integrating factors already. Okay, you've practiced integrating factors already. But what we've noticed is that certain differential equations can be solved by separating the variables, the separable differential equations. Some differential equations can be solved by using the integrating factor, but there are some differential equations that can't be solved using either of those two techniques. And what we want to look at is how to solve them in a different way that doesn't involve us using an integrating factor. Okay, and that's what we're going to look at now. So as I just said, there's some methods. Certainly in this case, I'll show you a way of solving this that's a lot more efficient. Okay, so just grab your notebooks then. So just before we look at how we could solve this using a different technique, we do need to just make sure we've got some understanding of some other definitions. So in your notebooks, just grab that down, and then just make sure you've got these two bits of notation down as well, please. So there is a difference between the language between the x part of your equation and the y part. Now the x variable, as you can see here, is the part that's on the bottom of the differential equation or the differentiation part. And because that's on the bottom part, on the denominator just there, that is what's called the independent variable. So the independent variable is the one that's on the denominator part of your dy over dx. Okay. No surprises then, the bit that's on the numerator, the y value, is called the dependent variable. So you have the independent variable which appears on the bottom and the dependent variable that appears on top. Now in most cases you will only deal with ones that have just a single independent variable and a single dependent variable. You can also get ones that have two dependent variables, and we'll be looking at those later on. So just get down what you need in your notebooks. Okay, so then we're going to go back to that differential equation that we did earlier on by using an integrating factor, and we're going to look at solving that in a different way. I'm going to solve it using a technique of splitting it up. So we're going to form a new differential equation to start with, and we're going to look at ones that consist of only the dependent variable. That's the one on the top. So I'm going to ignore anything that doesn't contain the y value. Right, so I can ignore the 6x squared, I can ignore the plus 3. In fact, what I'll do is I would put those to the other side. So if there was for example, minus 6x squared here, I would take that to the other side. Okay, so I've got just the numbers, or the ones that's got letters on top. So anything that contains a y as our dependent variable. All right, so when I say ignore, that means that these ones can just be set to 0. So I've got that. Now by doing that, because it's what we call a first order derivative, it's only got dy over dx, means that I can actually solve this now because it will be a separable differential equation. So I can separate it out and I can solve it. And I'd like you to pause there and just have a go at solving that differential equation using your standard math skills. Okay, so let's see if you manage to separate it out. So you can separate it out, and once you've separated it out, this is called the complementary function. The complementary function is the function you get by using just the dependent variables and setting it equal to 0. When you've solved it, you get a solution. You guys might have got the solution already from when you solved it by separating it, and the solution you've got is called the complementary function. So you always get the complementary function by setting it equal to 0 and finding a solution. Okay, so that's the complementary function. Check if you got your maths right then. So did you separate it out? Did you put your y's on one side, your x's on the other? Blah, 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 blah. Did you end up integrating it in terms of x? So you end up with this. And so therefore, this goes to obviously ln y. This goes to minus x squared plus c. And a little bit of rearranging, I can use the exponential function. And because it's plus c, that's going to come back to the a. So e to the c can go to just an a value in the front. So there we go. You should have got the answer. That is called the complementary function. In fact, if you tried putting that in and differentiating it there and adding two lots of 2x times that, you try that now, all right, putting that y value in there, differentiating it and putting it in there, and see what you get. There's no surprises that this bit would get you 0. Okay, that gets you 0. It's not what we wanted, but it definitely gets you 0. All right, we'll come back to why it's important in a minute. So that's the complementary function. Again, pause, take down what you need, make sure you've got that same answer down. Okay, but as we can see, that complementary function didn't get us an answer. It got us equal to 0. So what we want to do is get what we call a particular integral. Now, a particular integral is anything that actually works and gets an answer. So a particular solution, or a particular integral, not a particular solution, sorry, a particular integral, something that works. Now, sometimes you might have to guess this yourself, and there's some logical guesses we'll talk about later on, but sometimes you also get given an answer, or an answer that you've got to figure out the constant. So in this case, I'm going to tell you a possible solution. A possible solution is ax plus b. And the reason why that makes sense is that when you substitute that in, you're going to get something like an ax squared or a 2ax squared floating around here. So I'm definitely going to x squared because that's an x squared. Okay, I'm going to get, when I differentiate that, I'm going to get just a constant value. So I'm definitely going to get something when I add them together that's got x squareds in it, maybe some x's. I'm going to get some sort of linear function. Okay, if that was exponential or had sine and coses in it, clearly that wouldn't make any sense because you wouldn't get any sines and coses from this. Okay, so this particular solution definitely ties in to the answer we want. Now what I want to do is I want to just check it. So can you have a go at that yourself, please? You've got the y value as ax plus b. Can you stick it in there and times it by 2x? Can you differentiate it, add them together and see if you can compare coefficients? See if you can work out what the a and the b values are. Okay, so if you did that, then we could actually, you should have actually worked out your a and your b values for this to be true. So I've differentiated it. So there we go. I know that y equals ab. I know that differentiating just gets a. So really, I'm going to get a plus 2x, lots of ax plus b. I can neaten this up, can't I? There we go, by expanding that bracket. And now I'm in a position to say I know exactly what a is, because the only way I'm going to get x squared on this side is from this part of the function. So I can see that a has to be 3. And the only way I'm going to get the constant on its own, all right, no x values at all, is if b equals 0. So that part just there has been figured out using my skills. And also notice that the number on its own, the 3, fits as well. So we can see that this would be a particular integral. A particular integral that works in this case is y equals 3x. Okay, there may be others, but this is definitely one particular integral that works, and I only need one. Okay, so I've got my particular integral. Great. I've got my previous answer. Okay, my complementary function. That's sorted. One thing that's probably worth noting is very careful with my language. A particular integral is not the same as a particular solution. You've clearly heard of the word particular solution before. All right, a particular solution is a particular solution to the differential equation. A particular integral is a possible answer that works in there. Okay, one possible answer. So I'll come back to talking about a particular solution in a minute when we look at an exam question. Okay, so I've got two things now. I've got the complementary function and I've got a particular integral. I've got both of those things. And what I can do is I can get the general solution to this differential equation by just adding those two things together. So my complementary function that I worked out first by setting it equal to 0 and using separation skills. I can find the particular integral because I got given it and I can substitute it in and work it out. And now I can put them both together to get my differential, my general solution to this differential equation. In this case, y equals the complementary function plus the particular integral. And notice that is my general solution, and you already knew the answer because we did it earlier on with the integrating factor. Okay, so this is an alternative way of solving it, and although I had to discuss it all and go through what each of these things mean, hopefully you've noticed that that's a little bit easier than having to worry so much about all the integrating factor. It's easier just to do a separation, and it's easier to just find a particular solution, particular integral, sorry. Right, what's the difference with a particular solution? Well, a particular solution would mean that you know what that a value is, that constant just there. So you might be given a value, you work out the a value, and that would get you a particular solution. Okay, a particular solution. Right. What I'd like you to do then is spend some time just writing down that into your notebook. I've got an example of a particular integral there. I've got the differential equation and I want to solve it and I want to find the differential equation. I want a particular solution when x equals 0 and y equals 5. Okay, so just pause there. Have a go at doing as much as you can yourself. You might want to do all of it, it's up to you, and then we'll put the answer down in your notebook. Okay, so hopefully the first thing you thought about was working out the dependent variables, which is just the y's, and ignoring anything that's not got a dependent variable, so that's this side, and making that equal to naught. Okay, sometimes it might involve a little bit of rearranging, but in this case, we're just going to get dy over dx minus 3y equals naught. And that means we can work out the complementary function. Okay, we'll talk a bit in a minute about the order. You must get the complementary function first. There's a good reason for that, which you'll see later on. So you always start with the complementary function. Don't start with a particular integral. In this case, it doesn't make any difference, but it does matter in some questions, so be careful. Start with the complementary function. Okay, so that means that dy over dx minus 3y is going to equal 0. Right, so I'm looking for when that equals 0. So what I can do is I can certainly take that to that side, I can divide by the y, and I can use my standard math skills to separate it out and get a solution. Once I've done that, I can integrate both sides. I'm going to get 3x here, I'm going to get ln y there, plus c, rearrange, gets me a e to the 3x. It's quite common to get these exponential numbers coming through because it's very similar to the integrating factor we discussed in previous lessons. So I've got my complementary function. That's fine. Let me put that to one side. That's ticked off. What I can do now is deal with the particular integral. I need two parts to get my general solution. So I've got the complementary function. Now I want to look at the next. So I want to find the particular integral. Now they've told me in the question that a sine x plus b cos x is a particular integral. That means if I substitute it into here, it should be equal to 10 sine x if I can figure out the a and the b value. So what I'm going to do is, I definitely know what the y value is, that's fine, I can do 3 lots of it. I can also work out dy over dx, I can differentiate this. So let me do that first. So dy over dx is going to get me a cos x, because of course sine goes to cos goes to minus sine, so therefore that makes sense, it goes to that. Right, now I can substitute that in there. I can substitute that in there, and I can work out when it's equal to 10 sine x. So there we go. That's my dy over dx minus 3 lots of that, minus 3 lots of that, being careful with my signs, equals this. So what is my a and my b value? Now, because we're looking at the sines and coses, what I can do is I can work out the coefficients of sines and coses. So I know that, for example, a cos x minus 3b cos x has no cos x's on this side. So in other words, a minus 3b must be equal to 0. Whereas the sines, minus b minus 3a sine x must be equal to 10 sine x. So in other words, minus b minus 3a has got to equal 10. So that bit's going to equal 10, and that bit's going to equal 0. Some nice straightforward simultaneous equations. I trust you should be able to work those out yourselves. So I've got a equals minus 3 and b equals minus 1. So interestingly, this thing just here had the minus 3 sine x minus cos x that differentiates to just sine x because the cos parts will cancel each other out. Okay, so the particular integral that definitely works will be 3 sine x minus cos x. And in fact, I can now put these two together to get me my general solution. So if I put those together, my general solution is going to be the complementary function take away my particular integral, plus my particular integral. In this case, it's minus 3 sine x minus cos x. And what you can do there, you can just pause, and you could just try substituting that into this side. And hopefully, once you've done that, you'll see that it actually works out correct. So just pause, have a go, just convince yourselves. Okay, so what you should have noticed is the complementary function part cancelled out because it was equal to 0. That's why that bit is in there. It has to be in there because you're looking for a general solution. So this part is part of it. Okay, but it always cancels out because that's what you set earlier on. When does it equal 0? And this part, of course, parts of it will cancel out, leaving you the 10 sine x bit that you did want. Okay, so the general solution you should have found did work when you substituted it into there. Okay, so that's that first bit done. What I want to do now is deal with I've got the general solution, the particular solution, to work out what the A value is. Now I can do that, of course, by substituting the x equals 0 in and the y equals 5. So there we go. I can substitute both those values in. In this case, 5 equals blah, 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 blah with a 0. And my A will equal, 5 equals A minus 1. And so therefore A must equal 6. And I can put that back into my general solution. And there is my particular solution. And again, if you've tried substituting that in, it will definitely work because this bit will cancel out. Okay. So hopefully you can see that although it seemed more complicated earlier on, it is a lot easier way of solving differential equations than using the integrating factor. Okay, and if you are given a choice, you could get marks on either option. Right? You do not have to use the integrating factor unless they state it in the question. Okay, so just a few more notes for your notebook before we have a go at some of these questions. So a particular integral, we've just mentioned the particular integral that we can use. And in the previous two examples, I gave you a particular integral that you could then work out the coefficients. All right, so the first one was just a simple ax plus b, and the second one was a sine and cos function. But what you might need to do is you might need to think about working it out yourself. Okay. So just in your notebooks, let's just have a look at the three options that you could end up facing. It could only be these three, or it could be a combination of these three. So you might have a mixture of a polynomial and exponential. You might have a mixture of a trig and exponential, and so on. Okay, so let's have a quick look. So just pause if you still need more time on that page. Okay, so if f of x, if your function at the end has just polynomial terms, or has some polynomial terms, then the particular integral should always be a polynomial term up to the same order. You don't need to go beyond it, but you can't go less than it. Okay, so your polynomial term should always go up to the same order. Just be wary though, that in this case, excuse me, the y value is on its own. So therefore my y value should be up to an x squared because it's the same as that. If this has had an x in front of it, then you would use a function which is just bx plus c, because that x times the y would make it into an x squared. So just consider what numbers potentially, or what other variables are in front of the y. But this part just here should equal that. If you did accidentally use a quadratic and it should have been a linear, all you'll end up with is the a value equaling 0. So don't panic if you've got your polynomial function up to a higher order than you needed. It will cancel out in the end. It'll just save you some time. Okay, so I look at this solution just here. I notice it goes up to a quadratic. So my guess of my particular integral should be a quadratic polynomial function or quadratic function. Okay, if this was cubed, it would go up to 3 and so on. Okay, the other option, of course, is that it's an exponential. So a particular integral you should be using for the exponential should be another exponential with exactly the same power. So for example, in this case, if it was going to be 2e to the 3x, my answer should be ae to the 3x, some amount of e to the 3x. So that when I substitute it in here, I might find that after I've differentiated and added it, that a value might be something completely different, something like 5 or something like that. Okay, so you've got to use something that has e to the same power, and you've got a variable at the front, a constant at the front that you've got to figure out. Okay, that leaves the trig function, which we just saw actually. We just saw an example of this. So if you've got a trig function that's either cos or sine, your particular integral should have a sine and a cosine term. So even if this goes to sine here, your particular integral you should be trying should be a mixture of both sine and cos. Sometimes one of them cancels out, but as you saw in the previous example, even though that was just a cos function or a sine function, both of these appeared in our general solution. Now just be aware that you could have something like this. You could have 3 sine 4x plus 2e to the 3x. And so your particular integral in that case would be this plus this. Okay, so you can actually have combinations. You could have a combination of all three. All right, highly unlikely, but you could potentially have all three of those on this side, on the right-hand side of the differential equation, in which case your particular integral should be all three of those added together. Okay, right, so again, pause there, take some notes, because you've got to learn those off by heart and you've got to practice. So you can come back to this page, but try to learn them off by heart. Okay, so I'd like you just to have a go at that then. What's a particular integral? Look back at your notes and have a go. Be a bit mean, but just try it. Okay. Right, so hopefully, in fact, I've picked one that's exactly the same as what I just put in your notes. 2e to the 3x, your gut instinct would be to use ae to the 3x. And I would agree. That would be your starting position. That's what I would potentially start with. You try it and see what happens. But when you try it, there's a problem, isn't there? What is the problem? So have a think about it, substitute it in, see if you can work out what your A value is. Okay, so you substituted it in. If you haven't paused and substitute it in, you substitute it in and this happens. So the differential of it goes to 3a to the 3x. Minus 3 lots of it gets you 3a to the 3x. So when you do those two, they cancel each other out and get you 0. So my answer is 0 equals 2e to the 3x, which is absolute garbage, because it can't equal that. So in other words, ae to the 3x is not a particular integral, which is very odd, right? Because that contradicts what I just wrote down in your notebooks. But there's a reason why it doesn't work, okay? And the thing I told you earlier on is that you should not start with the particular integral. You should always start with the complementary function. And that's what I'd like you to do with this instead. Could you find the complementary function of the differential equation? Forget the particular integral for a minute. So pause there, set that equal to 0 and see if you can find a solution to it. Okay, so let's have a quick look at what your complementary function said. So if I've got dy over dx minus 3y equals 0, then the answer I end up getting for my complementary function is y equals ae to 3x. Now that's really interesting. And it's really interesting because, if you haven't noticed, both of those answers, the one you guessed for the particular integral and the one that came out for the differential equation, are very similar. They are both e to the 3x. So it is an unusual situation. It's not very common that your complementary function is exactly the same as your guess at the particular integral. But this is why I said you should always start with the complementary function. And if your complementary function comes out similar to what your guess would be, in other words, what's on the right-hand side, then you have to adapt your particular integral. It doesn't mean you can't do it. You've just got to adapt your particular integral. Okay, so you've got to spot that. It's very easy to spot because once you substitute, as long as you're checking it, some people might not spot it because they just write the particular integral. But when you try to work out what the a value is, the whole thing collapses. If that happens, don't just quit and think you've done something wrong. It's probably because you never spotted that your complementary function is similar to your particular integral, which is similar to the right-hand side. Okay, so what do you do then? Okay, grab your notebooks then. Let's just put down what we need to do in this situation. If the particular integral is a very similar form to the complementary function, so your guess at the particular integral is really similar to your complementary function. You know, maybe it's similar to your, if you've got something like your complementary function comes out to be cos 3x, then you wouldn't use a particular integral of cos 3x, okay, or a cos 3x. You would have to use something different. And what you do is you just put an extra factor of x into your particular integral. So we'll have a look at an example. That's the one I just did. So how can I go about finding the particular integral for this? Well, I need to start with the complementary function. We just did this, didn't we? The complementary function was y equals ae to the 3x. Once I know my complementary function, I should spot that my particular integral is similar to it. Okay, if you don't, then what's going to happen is you're going to get equal to 0, so then you will notice it anyway. But if you do notice it, what you need to do is you need to just change your particular integral. And the particular integral we're going to use is, instead of just a e to the 3x, which would be our guess, we're going to put this extra x value in. Okay, we'll put the extra x value in. Let's just see what happens when we do that. So we put this extra x value in, and we can work it out as we do normally. See if we can work out the a value. Now, last time we got 0, but this time when we do it, I have to be careful because I'm differentiating using product rules. So leave the x alone, differentiate the e to the 3x, leave the e to the 3x alone, differentiate the x, and so on. So when I do it, if I differentiate it, then this is going to be product rule, and this is just 3 lots of ax e to the 3x. What happens is when I differentiate this, I get this part, and notice that this cancels with that. And the reason why it cancels with it is the same reason why it didn't work earlier on. So now they cancel out. I end up with ae to the 3x equals 2e to the 3x. And so therefore my a value must equal 2. So that gives me my particular integral with an a value of 2, which means you can then find your general solution by adding your complementary function to your very similar particular integral function. And you end up with your general solution. Okay, so just be very wary. These things do come up. They've come up in an exam question before, so don't forget that extra bit. Now, usually, or hopefully, if you get a situation you're getting 0, you should be thinking, oh, that's one of those weird situations. Let me just put an extra x in. Okay. Right, have a go at the exercise 11A. Again, do not rush these guys. It's a good idea to have a go at nearly all of them. Make sure you're getting really used to working out the complementary function and then working out the integral, the particular integral, and then putting those together to get your general solution. Okay, so have a go at that exercise on page 252, please.